In the previous lecture, we have started to deal with the nuclear cell model. In fact, in that lecture, you have learned that the nuclear cell model is just similar to the Bohr model of electrons in the extranuclear space. By analogy with closed cells and subcells, in case of atoms, it is assumed that nucleons also form similar closed cells and subcells within the nucleus. We have seen that the neutrons and protons constituting the nucleus are supposed to be arranged in some type of cell structure, and all these cells get closed with a suitable number of protons and neutrons. From the compelling similarity of stability between the magic nuclei and the inert gases, it is assumed in the cell model that each nucleon moves independently inside the nucleus in a fixed orbit under the influence of a central field of force, or you can say a central potential V of R, produced by the average interaction between all the remaining nucleons in it. In fact, the simplest evidence you have seen for the nuclear cell model comes from the discovery of magic numbers. You know, the magic numbers you have studied that these are 2, 8, 20, 28, 50, 82 and 126. Now, the first aim of this cell model is to explain these magic numbers, and the simplest way for explaining the magic numbers is to assume that each nucleon in the nucleus moves freely in an orbit about the center of mass of the nucleus. In fact, this concept is known as independent particle model. And for dealing with this independent particle model, actually there are two suitable potentials, and those potentials are harmonic oscillator potential and the square wave potential. So today I am just going to start to deal with this independent particle model in this lecture by considering that the motion of our nucleon takes place in a harmonic oscillator potential. This problem can be equivalently deal with taking the square wave potential too, but I will assume here the harmonic oscillator potential to deal with the independent particle model. So now you know this independent particle model is a very vast concept. Our final aim in this model is to find the energy levels of the nucleons in the nucleus, and after getting the idea of energy levels, we will actually find the magic numbers. Since there will be a rigorous calculation, a long calculation, so for your convenience I have divided this lecture in two parts. In this first part of the lecture on independent particle model, we will see some of the important calculations by considering the harmonic oscillator potential both in Cartesian coordinate and in a spherical polar coordinate, although the spherical polar coordinate, the use of a spherical polar coordinate is more appropriate, you will see. And after that, in the second lecture, which will be actually the concluding lecture on this independent particle model, you will see the complete calculation of energy levels and the magic numbers. So let us start with this independent particle model, considering a nucleon moving freely or independently in the harmonic oscillator potential. Actually, that harmonic oscillator potential is spherically symmetric. This potential which we will consider is spherically symmetric. So first of all, taking this harmonic oscillator potential in which we assume that our nucleon is moving independently, first of all we will write the Schrodinger equation, that is the Schrodinger's time independent equation. We will start to write it. So what is this Schrodinger equation? You know, this is minus h bar square over 2m del square plus v of r times c of r equal to E times psi of r. You know this E is the energy eigenvalue and psi of r is the eigenstate or eigenfunction, or you can say the wave function. Since we are considering the harmonic oscillator potential, and you know in case of harmonic oscillator potential, the potential function V of r is equal to what? This is half m omega square r square. Here m is actually mass of our nucleon, omega is its cyclic frequency, and r is the distance. And as you know, in Cartesian coordinates, this r square can be written as x square plus y square plus z square. So you can say that this potential function V of r is equal to simply half m omega square x square plus y square plus z square. No. In fact, I have not solved this equation. You have, if you will see the course on quantum mechanics of my lecture, you can find this solution of this equation, and where you will find that when this equation is solved, to get the energy eigenvalue in case of the three-dimensional harmonic oscillator, then the energy eigenvalue comes out to be this much. In Cartesian coordinate, this energy eigenvalue is found to be n E equal to nx plus ny plus nz plus 3 by 2 h bar omega. In fact, as you know, in case of one-dimensional harmonic oscillator potential, E is equal to n plus half h bar omega, you know. And in case of the three-dimensional harmonic oscillator, this energy eigenvalue will be what? This will be just a superposition of the three terms. So instead of n, for the x degree of freedom, we write nx plus half h bar omega, and energy will be written as ex. Similar expression will be written for ey and ez. Don't confuse that this ex, ey, ez are components of energy. This is just a symbol. This is energy associated with the x degree of freedom with x motion. Similarly, there will be a degree of freedom with y motion and z motion. And when you will add all these energy terms, you will get the energy eigenvalue in case of the three-dimensional harmonic oscillator. And that energy expression is what? This is nx plus ny plus nz plus 3 by 2 times h bar omega. Now, if you consider that the sum of these quantum numbers nx, ny and nz is equal to this capital N, then what will be E? E is written as n plus 3 over 2 times h bar omega. Actually, here this total quantum number n is called total quantum number because this is the sum of the quantum numbers nx, ny and nz. And its values are integral values including the 0, and these values are 0, 1, 2, 3 and so on. Okay. So this is the expression for energy eigenvalue in case of a three-dimensional harmonic oscillator. As you can see from that result, that the energy eigenvalue E depends on the quantum number n, not on nx, ny and nz. As E does not depend on nx, ny and nz, so this result actually implies that there is a degeneracy of energy levels. As you know, the proton and neutron are actually fermion. When you say that proton and neutron are fermion, what does it mean? Actually, these particles obey the Fermi-Dirac statistics and they have a spin equal to half. And since its spin is half, so its magnetic spin quantum number ms will be equal to plus minus half. It means these particles has two possible spin states, which you call the up state and the down state. Okay, so each state is specified by these quantum numbers nx, ny and nz will have actually two possible spin states. And since these particles, proton and neutron, are actually the fermion, so they will obey the Pauli's exclusion principle. And so applying this Pauli's exclusion principle, we can find the number of proton P or the number of neutron N in a particular energy state. Actually, this number I have calculated here in tabular form. You can understand this table, how we can find the number of neutron or the number of proton. Actually, our aim is actually to find the magic number, and you know magic number is what? That is simply the number of either proton or neutron in a nucleus, which will be equal to either 2, 8, 20, 50, 82 and 126. That is our final aim. So how we can arrive the result to get the appropriate or correct magic number? For this, see first of all this table. Here in this table, in first column I have written the values of n, and then in second, third and fourth column I have mentioned the value of quantum number nx, ny and nz. And finally, in the last column I have written nn, which means the number of nucleon. This capital N is for number, and the subscript n refers nucleon. So this is actually the number of nucleon, that is number of proton or neutron. Actually, this number of neutron or proton, you will see after getting the result that it may be expressed as n plus 1 times n plus 2. So there will be actually two ways of finding this number of neutron or proton. So you can see, when we consider that n is equal to 0, and since this capital N is simply the sum of nx, ny and nz, and nx, ny and nz all are actually non-negative integers, so n will be 0 only when all these three will be 0. So in this condition, actually nx, ny and nz, all these three will be equal to 0. So there is only one set of the quantum numbers nx, ny and nz. But you know, when we will consider the spin state, so corresponding to this one set of nx, ny, nz, there will be two quantum states. It does one set of nx, ny, nz refers actually two quantum states. Why? Because one state will be a spin up state and another will be a spin down state. So you can find the number of proton or neutron simply by, there is one set of quantum numbers, so I have written here 1. And there will be two spin states, so 1 will be multiplied by 2. So 1 refers the number of sets of nx, ny, nz. This is one set, so I have written 1. And since there will be two spin states, so you have to multiply it by 2, and so that will be equal to 2. So when n will be 1, the number of neutron or proton in the nucleus will be equal to 2. Now consider n is equal to 1. When n will be 1, then actually there will be three possible sets of nx, ny and nz. And what are those three sets? You can see, if you consider that nx is 1, then ny and nz will be 0, because the sum should be equal to capital N. So you can see 1 plus 0 plus 0, that will be equal to 1. Okay. And similarly, if we consider ny equal to 0, then we have to take nx and ny, nz 0. And if you take nz equal to 1, then you have to take nx and ny equal to 0. So there are three possible sets of the quantum numbers nx, ny and nz. Okay. So, and each set will have two quantum states due to the two state of a spin. So number of sets of ny, nx and nz is 3. So I have written here 3. and number of spin states will be 2. So the total number of proton or neutron will be 3 into 2, and that is equal to 6. If you will use this formula to find the value of this nn, that is n plus 1 into n plus 2, then you make the calculation like this. N is 1, so n plus 1 will be equal to 2, and n plus 2 will be equal to 2 plus 1, that is 3. So this is 6. So I have actually calculated this number by considering the two ideas. First of all, I have written here the number in terms of this formula, that is nn equal to n plus 1 into n plus 2. And secondly, which is the actual state of affairs, that corresponding to each set of nx, ny, nz, there corresponds two quantum states. So from both ideas, I have calculated here the number of proton or neutron. Similarly, you can see when n will be equal to 2, then there will be actually 6 possible sets of nx, ny, and nz. In first set, you can take nx and ny equal to 1 and nz equal to 0. You can add 1 plus 1 plus 0, that will be 2. In second set, we consider this 1, 0, 1. In third set, we consider 1, 0, 1 and 1, 2, 3, 4, 5, 6. Oh, sorry. Here I have actually mentioned one column greater. So this is wrongly written here. You can see. So the another set is 1, 0, 1, and third set will be 0, 1, 1. And then if you take nx equal to 2, then ny and nz we have to take 0 because sum should be equal to 2. And the next set will be 0, 2, 0. And the last set you can take 0, 0, 2. You can see. So how many sets of nx, ny, nz? Tell me. Actually there are 6 sets, and corresponding to each set of nx, ny, nz, there will be 2 spin states. So the number of protons or neutrons, that will be 6 into 2, that is 12. And if you apply this formula, that is nn equal to n plus 1 into n plus 2, then what will be your result? You will get the same result. You can see, since capital N is 2, so n plus 1 will be 3, and n plus 2 will be 4. So this is again 12. So you can find the number of neutron or proton either by considering the total number of sets of nx, ny, nz, and after that we multiply it by 2. 2 is due to the spin states, 2 spin states, and or you can also find the same result by considering this formula, that the number of neutron or proton is simply equal to n plus 1 into n plus 2. Okay. So you can see, if we try to find the magic number, then how we can arrive the result. So first magic number will be 2, and after that you will have to add this 2 plus 6. So 2 plus 6, that will be equal to 8. This is the another magic number. And after that you have to find the magic number in this way, that will be 8 plus this 12. 8 plus 12, and that will be equal to 20. So in fact the sum of nn, when you will take sum of nn, then you will get what? 2, 8, 20. So first 3 magic number has been calculated even when you have considered the Schrodinger equation in Cartesian coordinate, and and you have written the energy eigenvalue. In similar way, you can find the other magic numbers by considering n equal to 3, n equal to 4, and so on. But I have not considered it here because the Schrodinger equation in spherical polar coordinate is more convenient and it gives more information. So now we will write the Schrodinger equation in a spherical polar coordinate, and then we will try to find the magic number by this independent particle model. So now let us see the Schrodinger equation, that is Schrodinger's time independent equation. When we will write it, it is del square psi of r plus 2m over h bar square e minus v of r times c of r psi of r equal to 0. Okay. Now in a spherical polar coordinate system, this Laplacian is defined like this. You can see here. And as our potential is harmonic oscillator potential, so you will write V of r equal to half m omega square r square. And you know the expression for the Laplacian spherical polar coordinate is this. This is 1 over r square del del r square del r plus 1 over r square 1 over sine theta del theta sine theta del theta plus 1 over sine square theta del 2 by del phi square. This is the expression for the Laplacian operator del square in a spherical polar coordinate system. But in the course on quantum mechanics, you have studied the angular momentum square operator, and you know the expression for the angular momentum square operator, that is L square operator, in a spherical polar coordinate is what? This is minus h bar square times 1 over sine theta del theta sine theta del theta plus 1 over sine square theta del 2 by del phi square. This is actually the expression for the angular momentum square operator, that is for the operator L square in a spherical polar coordinate system. So if you want to write the expression for the Laplacian in a spherical polar coordinate system, what will be that expression? You can see the first term in the expression for Laplacian remains at its. So I have written it just as it was in original expression. So you can see del square can be written as 1 over r square del r square del r. And instead of this second term, you can write minus L square over r square by h bar square. You can check from this expression for L square operator. If you will put it here, you will get the same expression for the Laplacian as I have mentioned it here. So in Schrodinger equation, instead of this del square operator, now we can use this expression for this Laplacian operator, which is 1 over r square del r square del r minus L square r square h bar square. Okay. So let us put it here in the Schrodinger equation which I have just defined. The Schrodinger equation will be now given as 1 over r square del r square del r minus L square over r square h bar square and plus 2m over h bar square times E minus V of r. But you know, in case of harmonic oscillator potential, this V of r is equal to what? This is half m omega square r square and psi r equal to 0. So this is this Schrodinger equation have been written now in terms of the angular momentum square operator, that is L square operator. Okay. Now you know, you have studied it in quantum mechanics that the angular momentum square operator, that is L square operator, has the eigenvalue L times L plus 1 into h bar square. You know, here actually this L is equal to 0, 1, 2, so on. These are actually the non-negative integers. Non-negative integers. And the eigenfunctions of this operator are spherical harmonics. All these things we have studied in quantum mechanics. The operator L square has the eigenvalues L times L plus 1 into h bar square, and the eigenfunctions for this operator are spherical harmonics, and these spherical harmonics is represented by the symbol ylm of theta phi. Okay, so if you want to write the eigenvalue equation for this L square operator, what will be that eigenvalue equation? You can see it here. This is your operator L square, and this L square has been operated on its eigenfunction, which is spherical harmonics ylm theta phi. When we will operate this operator L square on the eigenfunction ylm theta phi, we will get the eigenvalue of this operator, which is L into L plus 1 h bar square, and the same eigenfunction. So this equation 3 is simply the eigenvalue equation of the operator L square. Okay. Now, if you want to write the solution of this equation defined in equation 2, what will be its solution? As you know, this equation has actually two parts. First part, this is actually called radial part of this equation, radial part, and the second part is actually the angular part. Second part is angular part. Angular part means the part in which L square is included. So this is its angular part. So since it is a partial differential equation, so to get the actual solution, we have to separate the variables and then we get the solution. So actually the actual solution of this equation psi of r can be written as a product of the radial wave function, which is actually the solution of radial equation, and times ylm theta phi, which is the solution of angular part of that equation. So psi of r, which is the total solution of that equation 2, will be just a product of the radial wave equation, radial function r of r, and the spherical harmonic. Okay. Now, when we will use this expression in this equation number 3, in this equation 3, what will be in fact this L square operator have the eigenvalue L into L plus 1 h bar square. So instead of this L square in the equation number 2, we will write a small l into L plus 1 into h bar square. So when you will replace this L square by its eigenvalue, then this h bar square will cancel out and your result will be what? At that term, we will have L into L plus 1 over r square, and the other terms remain same. And if you want to write only the expression, only the equation for the radial part, then that equation 3 for the radial part will be what? This will be 1 over r squared del r, r squared del r, this much plus 2m over h bar square e minus half m omega square r square, r of r equal to 0. Okay. So substituting the eigenvalue of L square in the Schrodinger equation and writing that equation for the radial part, we get this equation 5. Now you know this wave function r of r satisfy a particular boundary condition. We have studied this actually in the case of central potential problem in quantum mechanics, particularly in case of the problem on hydrogen atom, that this r of r is equal to 0 when r tends to infinity, because this function is actually bounded. So when r tends to infinity, then r of r tends to 0 or it is equal to 0. Okay. Now applying this boundary condition and solving the equation, we get again the energy eigenvalue. I have not made here the total rigorous calculation because it is purely the subject matter of quantum mechanics, and you have already studied these things in quantum mechanics. So following that process, when we will find the energy eigenvalue, then what will be the expression, you have to remember it. You can see in this condition the energy eigenvalue E and L is found to be like this. E and L is equal to 2n plus L plus 3 by 2 times h bar omega. Okay. Actually here n is again 0, 1, 2 and so on. And you know L is called actually the orbital quantum number. This is orbital quantum number. Okay. Now if you write 2n plus 1 equal to capital N, then again this expression will be same as we have obtained in case of the Cartesian coordinate. So as we have seen in the case of Cartesian coordinate, that energy eigenvalue E is equal to n plus 3 by 2 times h bar omega. So comparing this expression for energy eigenvalue and this expression for energy eigenvalue, you can see that this total quantum number n is equal to what? This is 2n plus L. This is a most significant result. As you have seen in case of Cartesian coordinate system, that the energy of the oscillator depends only on the quantum number n. But here you can see when we consider the spherical polar coordinate system, we get an extra information that this energy eigenvalue actually depends on two quantum numbers. One is n and another is L. Actually this n is known as radial quantum number and L is called the orbital quantum number. So I have mentioned it here that the eigenvalues and eigenfunction in a spherical polar coordinate system depends on two quantum numbers. First one is the radial quantum number n and the second one is orbital quantum number L. Now this L, what will be actually the values of L when n is given? You can see that from this equation, if you try to find the value of L, L will be equal to n minus 2n. But you know n is 0, 1, 2, 3 and so on. So if we consider that n is even, what will be the value of L? When you say that n is even, the first value you can take 0. So when first value 0 and n will be also taken actually the if you take the values of n equal to 0, 1, 2, 3, then L will be equal to capital N in n minus 2, n minus 4, n minus 6. Now check it from here. If we take n even and if you take n even, take the first value 0. So n, this capital N will be now 0 and so L will be 0. Now take n equal to 2. This is another even value of n. So this will be in fact n minus 2, that is 2 minus 2, that is 0. And now take 4. Then you see that 4 minus 4, 0. So what does it mean? It means if you take the value of n equal to 0, 1, 2, 3 and you find that when we consider this capital N is even, then L is also even. For example, now take n equal to 8. Suppose that n equal to 8. This is an even number. What will be L? You can see. First value will be 8. See here. first value will be 8. Second value will be 8 minus 2, that is 6. Third value will be 8 minus 4, that is 4. Next value will be 8 minus 6, that is 2. So you can see this 2, 6, 8 and 4 all are these even numbers. So you can say that L can take only even values if n is even. And similarly, if we take n is equal to an odd number, then L will be also odd. Let us take for an example n equal to 7. N equal to 7 and 7 is an odd number. Then what will be L? You can see L will be, first of all, this will be equal to n, so that will be 7. Second will be n minus 2, that is 7 minus 2, that is 5. Third one will be 7 minus 4, that is 3. Okay. And last will be 7 minus 6, that is 1. So what you are seeing here? 1, 3, 5, 7. All are these odd numbers. So you can see when n is odd, then L will be also odd. Okay. That point I have mentioned it here. Now, the number of proton or neutron with a given value of n in this case depends on the quantum number small n, quantum number small l, that is the orbital quantum number. And you can find the total number of neutron or proton by this formula in this case. Nn equal to summation over L 2 times 2L plus 1. Actually, we will use this formula to get the number of neutron or proton in the next lecture. But remember it, if you have to find the number of neutron or proton, in this case, you can find this number by using this formula. Okay. Here actually again this factor 2 is due to the two spin states of our nucleons. Two states, up state and down state. So due to that two spin states, here this factor 2 is in this expression. Now, as you have studied earlier that in quantum mechanics, that the parity is defined as p equal to minus 1 to the power L, minus n to the power L. Now, you have seen just now that if n is even, then L is also even. And if L is even, then if you will put an even number as a power on 1, this p will be simply equal to plus 1. Minus 1 raised to the power any even number, that will be plus 1. And if p is plus 1, it represents actually even parity. So when the quantum number n is even, the orbital quantum number L will be also even, and we will say that the parity of all nucleons will be even. Even parity is also called positive parity, and it is denoted by the symbol I plus, where I actually represent the spin of the nucleon. Okay. And similarly, you can see if n is odd, then you have seen that L will be also odd. And when you will raise an odd number as a power of minus 1, for example, if you write minus 1 to the power 1, that will be minus 1. If you will write minus 1 to the power 3, this will be minus 1. So in that condition, the parity will be minus 1. Minus 1 means odd parity. And this is denoted by the symbol I minus. As a superscript, we write here sign of minus. And so when n is odd, then for all nucleons, the parity is odd parity. I have just told you earlier that this lecture on the independent particle model is not a complete lecture. I have not arrived the result from which we can calculate or which we can find or which we can obtain the magic numbers, but this is just a part of the complete lecture. And actually uh, using these results we will find the magic numbers or calculation of the energy levels of the nucleons in the nucleus in accordance with the cell model in the concluding lecture, which will just come after this lecture. So definitely you should watch the next coming lecture to complete this independent particle model.